Water is the most abundant substance on Earth, and yet billions of people around the world don't have enough of it. Today on the podcast, we're going to talk about H2E and Foghorn, two very different and yet weirdly related what-ifs, both about water.
I think it's just so rare to have a scientific moment where you're literally turning a valve and a substance is coming out and it feels like a miracle.
It was like literally this save the world juice.
That was something that just like really stuck with us because that directly related to the good that we could do in someone's life with this.
I'm Astro Teller, your host and captain of Moonshots, and this is the Moonshot Podcast. We're going to be talking today about doing something that sounds a little bit miraculous, getting clean water directly from the air. I've got Neil Treat and Claudia Truesdell with me. Thank you for joining us.
Thanks for the invite.
Yeah, thanks for having us.
Neil, give me the moonshot vision for H2E.
So H2E means hydration to everyone. And our aim was to provide the 2.2 billion people in the world, the water-stressed population, with a source of drinking water, and to get that by harvesting it from the air.
Doesn't seem like it, but there is a lot of water in the air. If we were to take all the water out of the air in the form of rain, it would cover the whole world with an inch of water. So it's not much percentage-wise, but it's quite a bit.
Can you kind of scope a little bit whether this is a small deal, a medium deal, or a really big deal?
Yeah, so I think whenever you look at the global water-stressed population, we're talking 2.2 billion people. So huge population. That's 1 in 3 people. And what that actually means is that a lot of people spend 1 in 3 people spend up to 50% of their income trying to get their next cup of water, drinking water. Sometimes the women and children can spend hours of their day trying to secure their next one. We went to Kenya to just talk to people and to listen to them. And we heard many stories about how a large amount of their cognitive load was actually trying to figure out where their next source of clean drinking water was. And so some people were talking about walking hours a day during the really dry season to be able to get the water. And so after that, again, think animals are sharing the same water hole, and that's a disease vector. And so what people would have is, chronic diarrhea and other sorts of gastrointestinal issues and just general discomfort that people would just live with.
You're describing the incredible number of person hours that it takes to go get this water. Mm-hmm. If they could somehow be freed of all of that time to go get that water, what do you think they would otherwise get to do? What's the opportunity cost here?
We had a great interview with someone who actually shaped a lot of the way that we thought about the project. So we met a lady while we were in Kenya. And when we asked her, what can you do with the device if you had something like this? Her response was, I'll never forget it. It was, I will level up my business. If I had a device like this, I could have more time. And if I had more time, I would be able to make more jute ropes. And if I made more jute ropes, I could make more money and I could reinvest that money into my business. And so what she was describing was not something that could help her, health-wise or time-wise or anything. She's linking it directly to an economic benefit that she wanted. So it was that was something that just really stuck with us, and why the cost was so important, meaning the cost per liter that we could target was so important because that directly related to the good that we could do in someone's life with this.
When you talk about the 2.2 billion people on the planet who are water stressed, where it would make a huge difference to them to be able to get a few glasses of water a day per person, mm-hmm. Where are they on the world, and how does that relate both to the amount of sunlight, which is a big source of power, energy, and also to the amount of humidity in the air?
So the 2.2 billion water stressed are mainly localized across Africa. So think sub-Saharan Africa and across India.
A lot of them are in places where there is no grid power, or grid power is very, you can't trust it. It's intermittent, which was part of the problem. So we couldn't run our device on electricity. We did a lot of work on finding where in the world such a device could be used, and then actually tweaking our design to be used by the most people in a certain region of the world.
So we're almost certainly going to need power, but you're saying a lot of these 2.5 billion people are where the power is unreliable. What about the humidity, the amount of water that's in the air, where those 2.5 billion people are?
So a lot of the work that we did early on in the project is to take geospatial population data and linking that with the surveys of where the water stress populations live. And then the third piece that we did is marry that with climate data. So we're able to see, and again, I think this is probably the surprising aspect that we found early on, was that more than 1 billion people lived in locations that had ample sunlight, ample humidity, and had access to no clean drinking water. So it was ripe for an atmospheric water generator. We published a report in Nature actually describing the data set that we constructed.
So essentially it proved, absent the issue of cost, that there was a real opportunity here, a real scale opportunity to change the lives of more than 1 billion people.
That's correct.
So, Claudia, we've been talking so far about a magic box, basically. Mm-hmm. We've satisfied ourselves that the magic box would matter to a lot of people, that the raw components like sunlight and some water in the air is available to this magic box. Mm-hmm. Tell us a little bit about making that magic box concrete.
Yeah, well, there are devices that already pull water from air. They're called dehumidifiers. They're pretty common. But we needed one that would work without electricity and would work in the conditions that we had identified. So there's different parts of that. We needed to have a very hot airstream. We knew that was one part of it. We needed to have a recirculating airstream that we increasingly make more and more wet.
It's like concentrating the humidity in a bit of the air.
In a bit of the air, and then constantly also taking then using that to harvest the air from it with condensation. And we needed those two airstreams to kind of both go through a desiccant material that would do the water transfer between them.
What's a desiccant?
A desiccant is a material that absorbs under certain heat conditions. It absorbs water, and then when you change the temperature of it, it desorbs. So
it lets go of the water.
It lets go of the water.
Think of it like a sponge.
Like a sponge, yeah, temperature dependent. So we actually had a really fun event very early on where we got I think we had like an hour or something, and we all had our foam core pieces and our we had some materials from our workshop, and we had a competition to see who could make a box that would collect the most solar energy the fastest. And that was a really great way to kick off the project.
It was really fun.
When you're talking about sub-Saharan Africa, most people imagine it's pretty dry there. What you just described, Claudia, sounds not easy, but like somewhat more doable in a really muggy place where there's a lot of water in the air. How little water could there be in the air, and this could still work, such that it then matched up with there still being 1 billion people who lived in places where it was like that?
Yeah, we targeted 30% relative humidity as our bottom.
And would I experience that as dry or muggy?
You would experience that as dry. Probably comfortable, but dry.
So you're going to make something that's going to take only sunlight and air that's just like sitting here with us, and somehow using only the sunlight, you're going to have to extract water. We must have had kill criteria. What was the threshold that we were challenging ourselves to get to?
So the kill criteria was it needs to be basically 1 cent per liter, because we believe that's what people could afford in terms of their daily water needs for a family. It needed to be affordable for people who made $2 to $8 a day and worked down to climates that were roughly 30% humidity.
How does it work on the inside? Like, go into a little bit more detail. Like, for example, when you take the sunlight, are you just using the heat from the sunlight, or are you actually turning the sunlight into electricity using a solar panel and then like using a machine, or some of both?
Mm-hmm. Yeah, some of both. We would do both. So the whole top surface of our device is really tuned to capture as much heat as possible.
It was multi-layer, and there was a film at the bottom. And the unique thing about the film is that it absorbed the photons and converted it really effectively into heat. So we're talking maybe 90% conversion. And the thing that surprised us the most at the beginning was the actual wattage output. So think like hair dryer is like 1,000 watts.
Yeah.
And this was putting out 1,200 watts just from a piece of plastic, a fan, and just something that you plop down in the sun. We actually thought it was wrong because if you look at the sun's photons, like there is 1,000 watts per square meter, and the device is a square meter. So it's not possible.
At the equator when it's properly pointed.
So that's not possible. Yeah. But the thing that we forgot about and we didn't realize is actually there's an extra element that we were absorbing, which is downwelling IR. So it's like things that are longer than visible light. Think about this as anytime you take like an incandescent light bulb and you feel the heat coming off of it, that's not visible light that's heating up your hand. That's actually the infrared spectrum that's coming off that black body radiation. And so anytime the atmosphere is heated up by the sun's photons, there's these IR rays are actually bouncing around everywhere. It's the reason why it feels hot. And so we were able to capture that longer wavelength, non-visible light and convert that into heat energy we could use in the solar thermal heater.
Nailed that part.
Yeah, it was great.
Yeah.
Worked really well. It started with these early prototypes that we did.
So you're describing that this box that's going to be pulling water from the air, the air needs to be hot and you need to be recirculating it. Can you unpack, like, why do we need to do that in the box in order to get water?
So part of the prototype that I worked with very directly was called the black box, and it was where the two airstreams came together. So we had a fresh outside airstream that came in, and we wanted it to hit a very warm desiccant wheel so that it can deposit its moisture into that desiccant. And then we needed that desiccant wheel to go through a very hot internal airstream and strip the moisture out of that desiccant material. So these two airstreams came together in this one box and were channeled through a rotating desiccant wheel that kind of had the surface of a cheese grater, which was significant to me because I was trying to keep them separate, and I needed to make a seal that could run on a rotating, moving wheel, cheese grater, and not disintegrate, but yet keep these two airstreams separate. So that was also another of my tasks that involved lots of prototyping donut-shaped objects out of multiple materials and then testing them.
Can we just pause on the desiccant, this sponge itself? We're talking like it's a single thing, but of course there's thousands of desiccants in the world. Did you have to invent your own? If you found something in the world, how did you pick that desiccant? How did that relate to all the other things that you were trying to solve for? Can you unpack that a little bit?
Well, we tried really hard to find, so first of all, like the way that we selected it is by taking the overlay of the water stress population with the climate of that area and understanding what, let's say, the overall climate would actually make the device most performant. So the actual selection was we needed to know what temperature and humidity the operating range would be for the rotor for the desiccant. And so basically what we were trying to find is at ambient conditions and ambient humidity, so down to 30%, it needed to suck up as much moisture as possible. And then at higher temperatures, what we could achieve in the solar thermal collector, so think like 80 to 120 C, that it needed to release the contents of its water and do that reliably. And so it's actually made from it's made from fiberglass. So it's a little non-woven fiber glass that's then impregnated with silica gel.
And is this something you found or something that you made?
So we actually have the whole gamut of stuff that we made to ultimately it's something that we partnered with another company who makes desiccant rotors for HVAC systems.
Tell me what the Mule was.
The Mule was like a fever dream of a mad scientist. It was an architecture that let us swap out any part. We've made all the different parts of the process separately and had them on a quite large table. It was roughly 5 feet by 12 feet or so, close to several thermotrons, which are these large machines that can spit out air in any kind of any humidity you want, any temperature you want. So we would be able to run the whole system as a system, but swap out components. So if we thought that we had a better way to collect the water or to transfer water from one airstream to another through a desiccant, we could swap out all those parts.
So it was sort of like a Frankenstein architecture onto which you could bolt any one piece of your system. You could test each part individually before you bolted them all together.
That's right.
Now, you're holding what we affectionately called a water bear because it looks a tiny bit like a water bear.
So our water bear was, it has an inlet and an outlet, which are just perfect for our crazy orange tubing that we had running between everything. And the inlet has a little filter to fix the air, to make it as laminar as possible. Laminar means all going kind of straightly in the same direction, not chaotic or crossing itself. Inside, it spins a small fan and it counts the number of rotations in order to figure out how fast the air is going. It's got 3 different ways of sensing the humidity in the air. It's got temperature sensors, and it's got a antenna that will send all of this data up to the cloud where we would track it.
What else do you have on the table here for us?
That is water from one of our very first prototypes, which was actually a dehumidifier that we hacked to work on solar energy. And it was the solar collector ended up being huge and nothing that we could actually put into a real product. But we did make water. So.
And look, there's algae in it, so
Yes.
it must be real.
That's been sitting there for about 4 years.
Yeah.
Well, that's kind of nice.
I think it's close to 6 years now. Yeah.
Oh, yeah. Because it was an early
'Cause that
one.
was the early prototype. I drank some of that water.
Would you still do
100%.
Pre-algae.
Pre-algae. I was going to say right now, no. But back in the day, 100% I drank some of the water.
I remember that you had several somewhat non-obvious problems that you also had to overcome in the design of this as you were going through these steps. One of the ones that I remember is, in principle, water from the air is super clean. It's perfectly clean. It's just H2O. But you had to worry about things like mold growing on the desiccant. Can you describe one or two of those problems and how you overcame them?
One of the things that you want to make sure that you don't do is have mold growing in it or other algae or other contamination that could come. And so we did brainstorm a lot of different ways to put, there are antibacterial coatings that you can place on different components. And so for us, the most critical component to put that coating was the condenser. Mm-hmm. That's where, imagine, you have this wet, cool, turns out exactly where algae wants to grow, environment, 100% humidity. And so we were designing coatings that could go over that component to keep mold from growing and fouling the condenser and then effectively poisoning the water that we were making.
But of course, every time you add something like a special coating, it adds cost.
Yeah, totally.
And so it's this fight between what you have to do to make this thing performative, so it's actually delivering on this sort of tiny local miracle that you're trying to accomplish.
Yeah, that's right. Yeah, it is really hard.
So if our goal was a penny a liter, amortized cost over the lifetime of a system, how close do you think we came in terms of line of sight?
Line of sight, I think we got to around 10 cents per liter. So we were about an order of magnitude off. Not too bad, but definitely within the realm of big things needed to change in order to get us down to the 1 cent per liter target.
We published all of our results, all of the things that we had designed. We put them all out there, and we described that we were asserting that we wouldn't assert any intellectual property rights. We were asking people to take these things and build on them. Can you describe a little bit of why we did that and how we did that?
The easiest thing to do would have just been to sit back and hold it. Because it actually took a lot of effort to document it, to write up the Nature article. And thank you to the editors for working with us on that and basically sharing that with the world. It's too big of a problem to hold back.
So is anyone building on it?
Yeah, there's a group out of Vietnam that has been in contact with us. They came and visited, and we gave them a tour of our prototypes and gave them some desiccant wheels to try out.
Very cool.
And answered technical questions that they had.
So I think one of the ways to look at it also is from the Nature paper. It's really, from what we can tell, it's become one of the more canonical studies on the location of these water stress and how it overlaps with climate. I think we've had 300 citations. I checked yesterday, so it was about 300 citations. And the most surprising thing is that half of them were from last year. So 2025, which is really amazing. So I was going to say it's continuing to accelerate and grow in terms of its impact.
So people are looking at this, but to best of your knowledge, no one has, since us, somehow figured out what we couldn't figure out. No one has figured out a way to make a magic box that would pull clean water from the air for a penny a liter yet.
Not that I know of.
No.
Do you think it's possible?
I'd say definitely it's possible. And I think that would require a new material. Those materials do exist. My understanding is that these are now, they're in the realm of academics. So I'd be academic lab has taken this material, they've invented something. So it's proof of life is amazing. And then you have a very long road ahead of you to try to make it actually work.
There isn't, at least today, a way that we know of to get atmospheric water for a penny a liter. Mm-hmm. But there are devices out there, even if they're nowhere close to that price point. Can you tell us a little bit about how they work?
Yeah, totally. There's a lot of different ways to capture water from the air. And a lot of what we were talking about was price and globally available. And so one example is actually fog harvesters. So think of those as just very cheap, well-engineered nets that they hang up into coastal foggy areas. And a meaningful amount of water actually is collected there that people use for drinking water, which is amazing. I do know that there are some more, I would say, expensive water harvesting equipment that's out there that is actually off-grid. So that's one of the examples. We also at the time heard about people putting larger atmospheric water generators that were not off-grid but required a grid hookup. And they were using it to capture water from the air so that they could be used for data centers. And at that point, again, what we're talking about here is a large installation. You need a large HVAC rotor, and you need basically an abundance of energy to be able to harvest the water from the air.
So cool, but not useful for the water-stressed people. You've both gone on to do a lot more with and for X. Maybe start with you, Claudia. How do you feel about having let this one go and continuing to sort of stay motivated and positive?
Well, I work in a central team called the Design Kitchen. My part of it largely helps very early stage projects with prototyping needs. My team is a part of so many projects, many of which do not go on, but we keep our eyes on the learning that we're doing, and we do it for the learning. And that just builds. My team gets richer in what we understand and know how to do and can make happen.
Neil, you have also spent a bunch of time at X. You're no longer at X. I hope you come back at some point. But you're at one of X's graduates, IO, which we talked about in another part of this same podcast, so listeners can go learn about that. What did you take away from your time at X?
My time at X is really punctuated by the factory and how the factory is an amplifier. One of the things that I realized early on is that you could have these let's say you could be heads down on your project, and then you step out because you're like, oh gosh, I need to get some coffee. And you bump into somebody in the hallway, and you begin to have these conversations that at some point they begin to be the nucleus of a new project. It's a unique experience to be a part of people that actually amplify your talent, what you know, and they make something so much better than what you could. And it's actually more lasting than what you would be able to do by yourself alone.
Neil, Claudia, it's been an absolute pleasure. Thank you for the work that you did. Thank you for the work that you're doing. Really appreciate you being here on the show.
Thank you, Astro.
Thanks, Astro.
It was fun.
It was phenomenal to hear from Neil and Claudia about their work on H2E. It's really exciting to see how their work may be living on in other ways after X. Next up, we're going to talk about the what if of Project Foghorn. Kathy Hannun is with us here today, and we're going to talk about something pretty incredible. Is it possible to take seawater and magically extract from it something you could burn in a gas tank to make your car go. Welcome back, Kathy.
It's good to be back.
Start with the story where we're all, a bunch of us, having dinner at my house. Mm-hmm. You were at the time a young, first job out of college, marketeer on Loon.
Sure. Yeah. As you said, X was small enough at that time that you invited all of X to your house for dinner, which was fun. And, one of the leaders at X at the time was talking about this paper he had read where some scientists had managed to build a device that would extract carbon dioxide from seawater. And the paper was talking about how one of the implications of being able to do that is that in theory, you could then take that CO2 and make it back into fuel. And all of a sudden you have sort of like a fuel recycling system where you burn fuel, it becomes CO2, it gets absorbed into the ocean, you extract it, and you make it into fuel. I thought it was an incredible idea. And so I asked, can I help with that?
There's so much to unpack there. But to be clear, this is a fuel and chemistry project.
Yeah.
And you had no fuel and chemistry background.
Admittedly, that is true. Also, I wasn't on the rapid evaluation team. But what that became in practice is I reached out to the lead scientist on that paper. It was a person named Matt Eisaman. And I invited him to come give a talk at X. And one of the great things about working at X is that when you extend such an invitation, more often than not, people accept. And so he came and gave a talk, and that's how we got started.
Matt ultimately joined the team, and the two of you kind of co-founded this project that became Foghorn.
One of the things I really loved about Matt from the beginning was Matt just has so much humility. So in his talk that he gave at X, he talked about the technology and the promise and sort of what they had achieved. And he also just talked just as thoroughly about what hadn't really worked and what he would want to improve if he was to continue the work. And the impression that made on me, I was like, this would be such an easy person to work with because he's telling us, here are the technical problems we would have to solve if we actually wanted to make this into something. And this was like the first time I had ever heard him talk about it.
We're going to have to get into the chemistry and help people understand it. Just pretend that there's a magical way to sort of take some stuff out of seawater and get a fuel we can stick into a car and burn. And the whole thing is carbon neutral. Pretend for a second that that's possible.
Yeah.
Seems a little bit too good to be true. Aren't we trying to get away from internal combustion engines anyway?
I think the central insight or the thought was while fossil fuels have some downsides that I think we're all kind of familiar with at this point, they're actually like magical, amazing substances. The energy density of a small volume of fossil fuel is incredible, meaning like your tank of gas in your car is not very large, and yet it can propel this very heavy car very fast for very long distances without needing to be refilled. And that's extremely convenient. And one could argue our entire modern lifestyle and sort of like most of what we've achieved as a human species owes some debt to that fact and that ability of fossil fuels to be such an amazing energy source. This was about 10 years ago. Yeah. So the thinking was we recognized that if we were able to invent a carbon neutral fuel that could fit into all the infrastructure already in place in the world, instead of having to retrofit all of the infrastructure in the world, that would be an amazing inversion of the problem. Reinvent the fuel instead of reinvent every car, every plane, every boat, every combustion engine out there.
So before we get into like mechanically, technically how, let's just make sure we understand the bits and pieces, the chemistry of this. Mm-hmm. So help us first with carbon dioxide. I think everybody thinks of carbon dioxide, CO2, as the bubbles in their Coke. Mm-hmm. It's a gas, so it doesn't stay in the water, they see it come out of the water. How do we get it out of the ocean?
So the ocean absorbs a lot of the carbon dioxide in the atmosphere, and it becomes carbonic acid in the ocean, which is why the ocean's becoming more acidic. And so the way that we got it out in this project was if you take some seawater and cause part of it to become more acidic, then some of that carbonic acid comes out of solution as carbon dioxide, and you can capture it.
How do we get from carbon dioxide to methanol that we can burn in our gas tank? Like, that feels like a jump.
It is, for sure. If you have carbon dioxide and you want to make it into a hydrocarbon, which is the chemical composition of these fuels, you have to combine it with hydrogen. There are many different ways to get hydrogen, but the conceptually simplest way is water is H2O, hydrogen is H2. So if you're able to cut that H-O bond with energy, you can make hydrogen.
So we had to do 3 things. If we wanted to actually turn seawater all the way into methanol, we would have to do 1, get the CO2, 2, get the hydrogen, and then you take 2 H2s and 1 carbon monoxide, you have to take an oxygen off, and you jam them together. That's the 3rd step, and then you have methanol. So you set out to build a machine that would do all 3 of those?
Well, luckily for us, the part where you combine the hydrogen and the carbon dioxide and create methanol or any other hydrocarbon was well established and did not need to be invented. The part where you extract hydrogen from water, it was not a mature technology, but lots of other people were doing it. And so the place where we really focused was the place no one was looking at, which was how do you get the carbon dioxide out of the seawater?
So when you started, there was going to be cost to each of these 3 steps.
Yes.
Did you focus the most on, as you just said, the carbon dioxide extraction part because it was the least understood, or because that's where most of the energy was going to go?
That was the focus because it was the least understood and it was the most expensive and sort of unproven. There were people that could just tell us how much it would cost to combine hydrogen and carbon dioxide to make different fuels. So that was known. And then on the creating hydrogen side, there was a cost curve because that technology development was underway. So while it was very expensive at the time, you could get some sense of like what that cost curve might look like over time. I remember one of the things that was emphasized at X was finding those technologies that looked like they were on that path. It's like, yeah, today it's very expensive to make renewable hydrogen, but it looks like it's improving quickly. And like, what will be possible in the world when those costs come down enough? Can we get ahead of that curve and be ready? And so we needed to know about that and do research on that, and we did, but our key focus was on the carbon dioxide part.
Early days, as you were starting up Foghorn, you tried to describe what would count as success here. I think you were the first one ever to write down what you called a kill criteria, but now we do that for all of our projects here. They all have kill criteria. Can you talk us a little bit about through the kill criteria that you had for Foghorn?
One of the things we were aware of from the beginning is that fuels are the ultimate commodities. There's a price of oil. It's like probably the most tracked commodity. If we wanted to have the scale of impact that X is really here for, we couldn't unless we got to a competitive cost. So we tried to figure out what cost per gallon do we need to be able to produce this fuel at in order for it to be meaningful. And
what was that?
We arrived, I think, at $5 a gallon, thinking that once you added all the costs of like the logistics and the transportation and everything else, you could probably sell it maybe at around $8 a gallon and be okay. And at that time, we thought you could get away with that price. Very high. I mean, just compared to other fuels, but there would be a big enough market for a totally carbon neutral fuel at $8 a gallon that we thought we could we could make this work if we hit that target. We decided that if we couldn't identify a path to $5 a gallon cost, we would kill the project.
So you build a machine, it was smaller than this office, and it's actually turning seawater into methanol. In this footage, we have mechanical engineer Jesse Revest explaining how the Foghorn system works in the lab in 2015.
When the water is very acidic, it lets that CO2 go easily. So this electrodialysis unit acidifies a stream of seawater to enable that CO2 to bubble out. But at the same time, we can use off-the-shelf technology to split the ocean water. So we get both CO2 out of the ocean water, and with an electrolysis unit, we get hydrogen. So we take those two streams of gas, and we put those into a chemical reactor. We compress them, we heat them, and we flow them over a catalyst. And as they flow over this catalyst, CO2 plus hydrogen turns into water plus methanol. We can then take that methanol over here. We can distill that mixture of methanol and water into 99.9% pure methanol.
We were collecting huge vats of seawater from nearby, and we had this contraption, like you're saying, and it was extracting CO2, and we made methanol out of it.
What were you feeling when those first couple of drips started coming out of the, like, almost test tube spigoty thing?
I think it's just so rare to have a scientific moment where you're literally turning a valve and a substance is coming out and it feels like a miracle. You know, it's just like you expect that in a cartoon maybe, but we were living it. And not only was it this project we had all put so much time and effort into, but the vision behind it was so inspiring to us. So, it was an incredible moment, just celebration, hugging, like shouting, just in a tiny cluttered lab in a basement somewhere, but I'll never forget it.
Yeah, and it was like literally this save the world juice. Mm-hmm. Like that's what it felt like at the time.
It did. It felt like a huge breakthrough. Right away, we ran into the problem of you have to use these very fancy, fragile membranes in the process of extracting CO2 from seawater, and they would get mineralized. They would get destroyed very quickly, and they were very expensive. So that was one of the first problems we ran into. But it was such a fun team. It was such a small team, and we were able to make progress against that problem pretty quickly. And that was just so exciting, to encounter a problem and then make progress and have that the dream sort of look like, okay, we're getting there.
So things were feeling really exciting. You'd made a lot of progress. What happened next?
Well, interestingly, one of the first problems that was not technical that we identified by having a kill criteria and tracking the dollars is, seawater is very dense and very expensive to pump. And pumping takes a lot of energy. There's carbonic acid in seawater, but it's pretty diffuse. It's a lot more concentrated than in the air, but we're still talking not that concentrated, which means you have to pump a lot of seawater to get the amount of CO2 you would want to make a fuel. So we basically realized, unless you're already pumping all that water for some other reason, it's just not going to work. You can't get to carbon neutrality if you have to use so much energy just pumping seawater. So that led us to desalination. We were like, who's pumping a lot of seawater? The desalinators are. So we actually made a trip to the United Arab Emirates. The Middle East has a lot of desal. And we're looking into how could we combine, and they are familiar with membranes. There were other reasons that it made sense, but how could we combine our process with an industrial process already pumping large amounts of seawater that also happens to have a great solar resource and potentially get the CO2 out that way?
So you had made this incredible progress on this really inspiring project. In the end, you decided to kill the project. Mm-hmm. How do you know the difference between, okay, the way we're currently doing it can't work, or we can't find a way to make it work?
I'll start by saying I don't think you can ever know. Opportunity cost is so high at X because there's so much opportunity at X. So like all the time and resource that you're spending working on one project is not going to the infinity other projects you could be working on. And I think over time, we were not identifying a path to $5 a gallon. We were very far from that number. And there were a lot of complexities. You know, like even that example I just gave, if your whole business model relies on partnering with desalination companies in the Middle East, that's going to be incredibly challenging. And it's already incredibly challenging because you have to like take on the technology of extracting CO2 from seawater, and renewable hydrogen wasn't there yet. So the complexities were adding up. There wasn't a clear path. And the opportunity cost was so high. And I think I just, even though I hated to see it because I was having a lot of fun and it was a great team and I was in love with the vision, it was clear to me this is probably not the project most likely to lead to the impact that we're looking for at X.
Was some part of you worried we were just going to banish you back to marketing, that you'd be in trouble somehow?
To your credit, really, I wasn't. I think you set the culture that came through clearly to me that there is excellence in setting kill criteria and building a model and then efficiently investigating the opportunity and then as quickly as possible making the call. I think we did have a meeting with you and other executives at X where the team presented our findings and what our logic was behind why we were recommending the kill. And you reacted so positively, right? So I didn't ever have a doubt I would be banished back to marketing, luckily. Or if I had that doubt, then maybe I would have been scared to kill it, which is the whole challenge, right, of creating that culture that celebrates the kill. The team disbanded, and that was sad for all of us. But for me personally, what it meant was that I had the opportunity to work on new investigations. I sourced an investigation that became Malta, which was a startup that spun out of X, and then also began the work on Tiny Lime, which was our code name for it, but it became Dandelion, which is the company that I started and am still working on today. So it led to really great things in the end.
You ultimately shared what we had learned and the ways we hadn't succeeded in Foghorn with the world. Can you describe that a little bit?
We wrote all of our work up and published it in a scientific journal called the International Journal of Greenhouse Gas Control. We published some of the business results and learnings in Fast Company, and then also went in a Harvard Business School case study so that at least we could share with the world, here's what we did, here's what we learned, in the hope that someday somebody could pick it up and run with it and make more progress than we had. And it turns out that many years later, my technical leader, Matt Eisaman, actually did pick the work back up. He joined up with one of our colleagues from back at X, Ben Tarbell, and they co-founded Ebb Carbon, which is leveraging that same technology as a carbon dioxide removal technology. Just
to take a moment, Matt passed away recently, and I know he was close to a lot of people at X, but probably you more than anyone else. Yeah, he played a big role in my early career, and I feel like, I was coming into this role, leading this project with no experience and no background that really set me up to do so. He was an incredibly accomplished professor, specialist in this area. And he always treated me like his collaborator and his equal. And I think it just made such a big difference to the way I saw myself at sort of critical time for me. I'm going to miss him. Yeah, he was a great human. And he was, as you said before, a really great Xer. He modeled this humility, not just because he was a good person, but I think he had deep intellectual honesty, which is what we're all trying to do here. Yeah. In some ways, like, he was the perfect
leader for the project to be able to embrace that kill criteria because he was so honest.
I'm so glad that you were here. We got to talk about actually two of the things that you worked on, but in a different part of this second season of our podcast, we're also talking about Malta. So even though I didn't get to talk to you about Malta, thank you for being one of the progenitors of that as well.
That's great. I'm so glad. I can't wait to listen to that episode.
I really enjoyed talking to both the H2E and Foghorn teams today. You know, as they went through their process, it was a little bit like X in microcosm. They worked hard on their moonshots. They got to the place where winding down their moonshot was the right thing for X and for the world. They shared what they were working on with the world. The world found ways to pick up where we left off and to continue moving those opportunities forward. Two of those three people stayed at X, started new moonshots, spun out with those, and are now working on those moonshots on the outside. And Claudia is still here at X in the design kitchen, working to spark future moonshots. Next time on the Moonshot Podcast, computer chips are the silent beating heart of the modern world. Our ability to make those chips and to feed those chips with electricity is falling off of a cliff. We'll be exploring radically different ways of designing and building the computer chips of tomorrow.
If cars did what chips did, 50 years of Moore's Law, then you could drive to the sun in 1 hour on 1 gallon of gas.
We were building the hardware for artificial brains and we had to be together. It was fate.
This is the Moonshot Podcast, a peak action production for X, the Moonshot Factory, with me, Astro Teller. You can find more episodes wherever you get your podcasts and on our YouTube channel. If you want to take your own moonshots, we've developed a masterclass certificate course. Check it out in the show notes below. If you enjoyed this podcast, don't forget to subscribe. It helps other people find out about this series.